it is time to discuss the transition between the Pythagorean theorem and trigonometry. This is a major transition that often takes place, say, during junior year of high school. So to start with, the Pythagorean theorem states that for any right triangle, you have the relationship that a squared plus b squared equals c squared. Okay? And so the idea here would be that if you know two of the sides of the triangle, then you can use the Pythagorean theorem to get the third side. Now, this is called the distance formula because it's actually used in most of the sciences and, like, say, in the real world, meaning the world where math and science are actually used to compute the distance. And the reason why is because, like, just to give you an example, let's say you want to compute the distance from this point to this point. Well, you have two options. You can measure that distance, okay? And if you can just measure it, you don't need the Pythagorean theorem, you just measure it. But in some cases, you might not be able to directly measure it. Instead, what you can do is put a coordinate system out there and often get the vertical and horizontal distances of that measurement. And note that here I've constructed a right triangle. It wasn't there to begin with. And so with the coordinate axis, it could be that this is a side of 3 and this is a side of 4, and I want to figure out the unknown side. Now, the labels A, B, and C could be anything. They could be X, Y, and Z. It doesn't really matter. So if it's an unknown side, you could call it X, or you could call it C to be more suggestive because it's often written in terms of C. And so in this particular case, I can try to solve this right triangle now using the Pythagorean theorem. And so I can say that, for instance, 3 squared plus 4 squared equals c squared. And then what I'll get here is I get 9 plus 16 equals c squared. And that's going to give me 25 equals c squared, which is the same as 5 equals c. Okay? So this is actually a special right triangle because it's all whole numbers. And that's called a Pythagorean triple. And so when you have a Pythagorean triple like 3, 4, 5, it could be worth memorizing that one because it is actually like the first one. It's kind of like counting, right? Like the first 3 numbers are 1, 2, and 3. The first Pythagorean triple is actually 3, 4, 5 because you can actually have a smaller one, where I'll say all the numbers are smaller. Okay. Let me give you another example. So let's say that let's go over here, and let's say I have something like this. So what if this side is 1 and this side is 2? Now, in this case, note that the unknown side would be quote A or B. I say quote because variables doesn't really matter. And also note that in the Pythagorean theorem, A and B are actually interchangeable, right? The key is that C is the hypotenuse stands alone, and the hypotenuse is opposite of the right triangle. So here's the right triangle, and opposite that is side C. A and B are connected to it. So in this case, if I want to solve this, I would use 1 squared plus b squared equals 2 squared. I get 1 plus b squared equals 4. Get the b squared by itself. That's subtract 1 from both sides. B squared equals 3. Now, there is no whole number that you can square to get 3. Okay? If you look at the original problem here, this is obvious because, right, the hypotenuse 2 is the largest of the 3 sides. Okay? And I guess the idea here is that it's got to be in between 1 and 2. Okay? And it turns out so what do you do in this case? It's actually easier in math because the exact answer then what's the square root of 3? And that's basically by definition that you get the square root. Like what's the number? It's the square. When you're solving the square equals a number, the answer is the square root of that number. Like we could have that here too, say c equals the square root of 25, but in that case we can simplify it to a whole number, which is 5. Okay? So this is basically how the Pythagorean theorem works. Now, the key to make the jump to trigonometry is to identify one key property, you could say, and it's that similar triangles have sides that are in proportion to each other. What does that mean? Well, let's look at these two examples. So look at the 3, 4, 5. If I double these in size, okay, try that here. You know, and I say, well, okay, this is 6 now, and this is 8. Okay, now do I know what C is here? Well, if you look at these two triangles here, they're actually in proportions because 3 is to 6 is 4 is to 8. In effect, the bigger triangle is double the smaller one. So if you know that the smaller one is 3, 4, 5, then you know this one is 6, 8, 10. And you can actually use the Pythagorean theorem to check that. 6 squared plus 8 squared, that's 36 plus 64 is 100, and 10 squared is 100. Okay, so the Pythagorean theorem is like a safeguard, it checks out. But this is a big step because the idea is that when you have certain properties within a triangle and you scale that triangle to larger or smaller, the ratios of the sides are the same. And that is how you get into trigonometry. So here's the difference, okay? Pythagorean theorem, we need two sides, okay? And it gives us the third. But let's go up here to this example now. We just solved that b is the square root of 3, okay? It turns out that this is a special triangle like the 3, 4, 5, okay? These are probably the two most important triangles in geometry. The 3, 4, 5 is by example, but the 1, 2, root 3 is by the angles, okay? I don't actually know what the angles are for the 3, 4, 5. We could use trig to figure that out. We're not going to, maybe at a later time. But I will just tell you that this is a 30, 60, 90 triangle. And so this side is 30 degrees and this side is 60 degrees. Okay? So what is that? Why is that important? Well, you're going to see in a little bit why it's important. Okay? Because let's just take the example down here. All right? Let's say I have another 30, 60 triangle, but maybe it's larger. Now, these triangles are often not going to be drawn to scale, right? So it could be like, this could be 10 times as big because we're not concerned about the units and trying to draw them precisely. The drawing should just be indicative of the reality. So in this case, what do I want to do? I want to say that well, this one is 30. I could stop there because the reality is that if that's 30, the other's got to be 60 because triangles sum to 180 degrees. So if one is 90, the other two must sum to 90 also to give 180. So I don't need to mark that the other one is 60. And let's say that this is 2. Okay? Here's what I want to tell you. By that alone, which is really one angle and one side, using, quote, trigonometry, you can solve the entire right triangle. Okay, so how do you do that? Well, there's some different ways, but to start with, the key way is that you actually know the relationships between the sides of, say, the 30, 60, 90 triangle, which I gave you up here. Okay, so you can see that these two are basically a match, right? They both match 30, 60. We can easily solve this angle as 60. And now the question is, what about the other sides? You know, how can I get what in this case might be like B and C? Okay, well, let's compare it to the other triangle. Because these two triangles are similar, all triangles that share the same angles are in fact similar, the sides are going to be in the same ratio. So there's some cool ways you can look at it because you can look at it both from one triangle to another or within. So if I look at it within this top triangle, the small side to the large side is a doubling. It is actually a times 2. Okay, so I can use that same strategy here. If I go from the 2 to the largest side, it is a times 2, and this becomes a 4. Okay? So I'm just using similar triangles here. And furthermore, the other one's a little trickier if you're not used to how to do this. So you see a 1 and a root 3. And the question is like, wait a minute, how do you go from 1 to root 3? Well, it's actually 1 times root 3. So to go from the small side to the larger of the two legs, it's times the square root of 3. Because 1 times square root of 3 is square root of 3. And so here you're going to go 2 times the square root of 3. This is actually 2 root 3. Okay? If you understood that example, you are in great shape going forward. Okay? It's really important, so I'm just going to go over it one more time. I'm giving you basically the first triangle, that all 30, 60, 90 triangles have the sides in a ratio of 1, the smallest side, to doubling that, a 2 for the largest side, to the side in the middle is the smallest side times root 3. Now I say all these different sides, but I think the best way to look at it is really the way it was done here. You go from 1, you double it to the hypotenuse, and you multiply by root 3 to the larger of the two legs. Okay, A and B are considered the legs and C the hypotenuse. So to go from down here then, right, you double the 2 because it's opposite the smaller side to get the 4, and you multiply the 2 by root 3 to get the larger side, which is 2 root 3. Okay? So really all this is similar triangles, right? It's nice and it's important. So I'm actually going to do a couple more. Okay? Let's leave the Pythagorean theorem behind. And while I'm clearing this, I do want you to note that there is a significant difference here. And in the Pythagorean theorem, the idea is that you've got to have two sides typically to make progress. But with what we just did, we only had one side, okay? We had one side of a right triangle, and we used that to actually get the other sides. The key was that angle. So what trig allows us to do is solve triangles given one angle and one side. Pythagorean theorem, hey, you got two sides, use that for the third side. But if you have one angle and one side only, you need trig. Let's do another example. Okay, so let me give you some tips on constructing these. Okay, first of all, one side is clearly shorter than the other, okay? I usually set mine up like that. And then I just, beyond that, you just try to connect it. And it's got to be a right angle. All these theorems only work for right angles. But you saw from that example, a distance between 2 points, you can almost always construct a right triangle to figure out the distance. And this is real, you all. This is not like some, oh, when would you do that? We're talking like, how do you figure out things like the distance to the moon, or say the distance to the sun if you know the distance to the moon? Okay, right triangles, right? So this is a really powerful way to figure out distances that you could not like measure by hand. Like clearly no one's going out and like walking to the sun to measure it. By the time you got close enough, you would evaporate because the sun is very intense. And you'd also have to get there somehow. Okay, so the idea here is that I'm going to tell you one of the angles. Like in this case, now look, in this case, they're basically set. If I want to do a 30, 60, 90, which I do, this is the smallest side. So your 30-degree angle has to be opposite to it, which makes it here, okay? And the longer of the two legs, that's this one, then is opposite the 60. And now I'm suggesting, okay, I give you one side, you can get the other two, all right? Let's say that I give you that this side is 6. How about 6? Okay? And now you've got to figure out A and C. So how do you do that? Well, you need to use the relationship of the 30-60 triangle that is displayed here. Okay? You say, well, okay, if the largest side, whatever it is, if I'm going in reverse, the small side is actually half of that, right? You go from 2 to 1, you go in reverse, it's divided by 2. So I divide by 2 to go from 6 to this side, I get 3. And now once I have that, right, I don't need to do a roundabout way. I can go from this side, I just multiply by root 3 to get this side. That's how you always do it. 3 times root 3. You just write it like that. I call that one C. Usually that would be called B here, and C would be the hypotenuse. But the variables are interchangeable. But, for the sake of clarity, I'll just call that a B. And my B's look like 6s, excuse me. Okay, so this is a general idea. So what you're expected to do here is memorize that triangle, okay? I'm going to do it again because it's so important. It is, I would say it's along with the 3, 4, 5, which is just a Pythagorean triple to keep in your mind, this is actually the most important triangle to memorize, and frankly, the only one you need to memorize. I'm going to show you another important one in a minute. But again, to do this setup, just do a short leg, make a longer leg, connect. And the idea is this. You could use any 3 numbers, so you want to use the number 1, right? Because 1 is the nicest to multiply by. So which one would you pick for 1? Well, naturally, you pick the smallest. See, you're free to always pick a 1 when you're constructing something because, right, they're all similar. So, right, I could pick any number for this one. I could pick 3/4, right? But who wants to deal with fractions? It's nice to pick 1, number is 1. And why can we do that? It's because units are always different. Like, is it feet, inches, centimeters, meters, nanometers? Like, could be anything. So I just call it 1. That's opposite my 30. The smallest side opposite the smallest angle. And the key is to try to remember 2 and root 3. Okay, like those numbers in your head. Because if you have those numbers in your head, they have to go in certain places. Why? Well, the key is to look at them all in terms of roots. So I know that 2 is bigger than root 3. Do you know that? You might not. How do I know that, right? What's justification for that? It's to put everything in terms of square roots. Square root of 4 is 2, and the square root of 1 is 1. And now you have a fair basis of comparison where it's clear what the ordering of the sides are, because root 1 is clearly the smallest, root 4 is clearly the biggest, and root 3 is clearly in the middle. But no one ever really writes root 4 and root 1 because they'll simplify to 2 and 1. Okay? So we don't need those roots there, but what you need to do, it's kind of nice to look at it like that, is memorize this triangle. And if you memorize this triangle, you can solve every 30, 60, 90 triangle. Okay? Put a big box around it. I'm gonna write memorize, okay? Because I'm not big on memorizing, but this is one that you want to memorize. Okay? And with practice, like you'll get it down eventually. Okay, so if you know it, what do you do with it? Right? I mean, we've been solving, okay, and we can look at some other things to do with it. Like, for instance, you can consider, what about the sine and the cosine and the tangent, and what actually are those things? Okay, so we'll look at those in just a moment.